Okay. Just give me a second. Let me check. The document isn't getting open. I'll just have a check. Okay. Okay. So, yeah, that's from here. Uh, Able to see this doc, guys? Guys, are you able to see the document?
Yes, ma'am.
Okay. All right. So yeah, we are going to study about quick sort. So before I teach you quick sort, let me just take it with a very lame example. Assume that you have a class, in your class, you have girls who are of different heights, right? So if in case I ask you to stand in the order of your height, okay, assume that there are some set of girls here, some set of people here who are of different heights, and then you're asked to set yourself in terms of your height. So what happens? The person who knows that they're shortest of all, they themselves will take their position in the first place. And the person who knows that they're the tallest among all, that person would definitely go to the last without even talking to anybody or thinking about anything, right? And the remaining people, they have to check with each other or discuss among each other, or somebody should point out to them who should move front, who should move behind. So that movement should happen with the people in between. But the first one and the last one, I mean the shortest and the tallest, will take their own positions rather than depending on somebody. But the rest of them need to ask or figure out among each other, right? So this is one such exam. So what did they do? The first and the last were quick to take their positions. The middle ones who has to take the position needed some technique here. So the same implementation is done in quick sort algorithm. Okay. Now assume that you have some set of numbers. If you can look at these numbers here, it's like 10, 80, 90, 60, 30, 20. So you see that the smallest of all is in the beginning. So it is already sorted. Coming to this one, take the second example. You have numbers like 6, 3, 5, 4, 2, 1, 9. The biggest of all, the bigger number of all, 9, is at its already sorted position. All right. Now, if you take another example like 4, 6, 7, 6, 10, 16, 12, 13, 14. Here, if you look at 10, it is in a sorted order. Why is it in a sorted order? The number lesser than 10 are all to its left. The numbers greater than 10 are all to its right. Whether they are in sorted among themselves, that is secondary. But for now, 10, when we assume 10, 10 is 10, it is in its own position. I hope you all understood till here. Yes or no? Just answer via chat. Anyways, let me go ahead. So yeah, now let us consider some elements here. So in order to, I'm trying to solve quick sort now. So let us consider there are some numbers, some elements. You get to see that there are some numbers filled over here, but the last block, it is put with an infinite symbol. Why is it put? Off late you'll get to know, all right? But for now, we are taking one extra position. So ma'am, is it always to take over here? No, not mandatory. If you want to take, put a block here and take one empty symbol here, any symbol here, you can even place it over here. So any one place you keep a block extra. So here, since we are representing infinity, and we also know that the numbers greater than greater should be going at the right, infinity, that's the reason kept at the right. All right. So here what are we doing? We are considering these elements. We are taking the first element to be first index position to be low and the last index position to be high. All right. And now we are maintaining two variables called I and j, which generally you know that we maintain it to handle the loops. So we are maintaining I variable and j variable. All right. These are the two variables that we will be using. Why we use I and j, you guys still now might have understood after seeing so many algorithms. Now the next rule when we are doing quick sort is we have to consider one of the element as the pivot element. What is a pivot element? Pivot, P-I-V-O-T. Okay. So you have to consider one of the element. Here it is. One element is a pivot element. Why do we have to consider it? We are assuming one. Like say for example in your class, if they are a set of girls, so when you're taking someone's help to decide where that person's position should be, now you are deciding where that person should stand among the girls who, depending on their height. So what does the elder person, I mean, assume that your ma'am itself is standing. So what does your ma'am do? She considers that girl and she compares the girl among the students standing over there and sees where her right position would be. So now that girl for timing becomes the pivot. I hope you're understanding what is the meaning of pivot. The element that you are considering to push it to its original position is not, that element is considered to be a pivot element. All right. And so over in quicksort, you have to maintain one pivot element. All right. So for now, what are we doing? We are considering the first element over here, that is 10, to be your pivot element. All right. I and j is to refer to the index position, but pivot refers to the element. Again, remember, I and j represents the index position. What is index position here? If I represent this to be 1, this to be 2, all right, 3, 4, these are your index positions, right? 10 here is the pivot element, not 1. Element is pivot, all right? Now, so what are we doing for now? We are taking 10 to be our pivot element. Ma'am, is it mandatory to take the first element only? Not mandatory to take the first element. Any random element can be picked, all right? So for now, I have taken 10. Okay, now, what does this I and j do? When you fix one pivot element, I and j is basically used to search elements greater and less than this pivot element. That means here I will be searching for an element which is comparatively greater than the pivot element. J is one variable which will be searching for elements which is less than the pivot element. So pivot element matlab 10. So I should search numbers which are greater than 10. J should search numbers which are less than 10. Hope it is clear till here. Again, I'm repeating. I is a variable that searches numbers greater than 10. J is a variable that searches numbers less than 10. Now, I guess it's clear till here. Now, besides finding all these things, how should I and j be moving? I is placed at the first location and j is placed at the last location. Okay, I is placed at the first location, j is placed at the last location. I keeps on incrementing. As and when it increments, it keeps searching for an element greater than its pivot element. J keeps decrementing. Till when does it decrement? As and when it finds element less than the pivot element. This is one thing. Another thing that it does, till when should it search? As long as the index position is I less than j, till then they should get incremented. Again, remember, the I should get incremented, j should get decremented, right? Till when should be they doing it? As long as I is less than j. So what is I, what is j? That index position should be less than each other. You will understand it when you start doing a problem on it, okay? No, so for now, if you take this, if you assume this elements as your example, and now these elements are there, you have considered 10 to be your pivot element, and you want I to search an element greater than 10 and j to search an element less than 10, right? So look at this now. Here you have certain elements. You have I here, you have j here, you have considered this as your L low, and this is your high, that is h. So increment I, you will increment this I, it goes to the next place, and it checks whether it is greater than the pivot element or not. In the meantime, j gets decremented. It also checks whether it is less than pivot or not. So that means what happens here? I, which was over here initially, it moved to the next position, so it came over here. J, which was over here initially, it moved over here, so it came here. So here we find that I is greater than the pivot element, so is j less than the pivot element. You're able to see this, right? It is 16 greater than 10, 5 less than 10. So immediately when you find such elements, you will swap them. So you will swap 16 with 5. You will not disturb 10. 10 is still your pivot element, it is holding, because it has to find its original position. So position is not caught still. All right. Now this is over. So 5 comes here, 16 goes there. It's done. Now again I has to increment, meanwhile j has to increment. When I increments over here, I came over here, it found 8, but 8 is comparatively smaller to 10, so I will not remain here, it has to go further still. Similarly j, it comes over to 9, it checks whether j is less than 10. Yes it is. So for now you will find I towards 12, j towards 9, right? So I, which came over here, it did not find it to be smaller than 10, so it moved further, it stopped at 12 because 12 is comparatively greater than 10. Here 16, it was earlier at 16, it got decremented, came at 9, it found 9 is less than 10, so it stops here. Now what should happen? This 12 should get swapped with 9. Clear? 12 should get swapped with 9. So 9 comes here, 12 goes over here. So 9 came here, 12 went over here. So this is what it has there. So for now again, I is at 9, j is at 12. Again it gets incremented. So I comes to 15, j comes to 3. When they come over here, it finds that I has found an element greater than 10. Meantime, j has found, when it comes to 3, it found that it is less than 10. So it is over here now currently. So it sees that the condition applies, so they have to get swapped. It gets swapped here. So 3 comes over here, 15 goes over here. So 3 came here, 15 came here. Now I has to get incremented. I goes to 6. When it goes to 6, it finds that it is less than 10. It has to get incremented again. So I comes here. So I should be over here. Now j, it comes over here. It sees that yes, it found an element less than 10. Okay. I moved on to this place and j moved here because it did not stop here. I did not stop here because it is not greater than 10. J, it found an element less than 10. So therefore it stops here. Then I earlier told that till where should this increment continue? Till as long as I is less than j. Right? I just told you that this incrementing and decrementing of I and j should happen as long as I is less than j, as long as it is less than j. So if in case I comes over here, as it came just now over here, if in case I comes here, the index position of I becomes greater than j. Yes or no? Because this is 1, 2, 3, 4, 5, 6, 7. So this became 7 and j became 6. J became 6. So the condition goes false. You cannot, I told you that I should be less than j. So you will not do any swap even if you find that a number should be reduced. I mean, the number should get swapped, the number is small or greater. You will not because the condition failed. Now, where should I put the pivot element then? At the place where j stopped. The j has stopped over here. So you will consider this place to be your pivot place. That means what will you do here? You will shift j, the pivot element, in place of this 6 and shift 6 to this place. Understanding it or not? So here 6 comes here, 10 comes here. Now what you find? 10 has come to its original place. 10 has come to its original place because all the numbers less than 10 are to its left. All the numbers greater than 10 are towards its right. Is that clear or not? You want me to explain again? Okay. Okay, one quick recap I'll be doing. Once again, concentrate. First, you will take certain elements, some random elements, any elements can come in, okay? First job, what you have to do is make one element as your pivot element. Any number can be made, not mandatory that it has to be the first number. Any number can be maintained to be your pivot element, all right? So we have considered 10 to be your pivot element. Then you're keeping two variables, I and j. Where do you locate I? I at the beginning of an array and j at the end of an array. I is to increment and j is to decrement. I gets incremented and j gets decremented. Okay. As long till when should they get incremented and decremented? As I just told that as long as I is less than j, it has to do this job. So what is I and j referring to? They are referring towards the index position 1, 2, 3, 4, 5, 6, 7, 8, 9 and so on. Okay. Now, when I gets incremented, the rule is when I is incrementing, it has to search an element which is greater than the pivot element. Now that we have considered pivot to be 10, so I have to search elements which is greater than 10 and j should search an element which is less than the pivot element. Since for now pivot element is 10, j should search elements less than 10. That's the rule. Okay. Now, I gets incremented. Earlier I was here, it moves on. So I came here. J has to get decremented. So earlier it was here, it has to come at 5, it came over here. I found an element which is greater than the pivot element, that is greater than 10. Meanwhile, J found an element which is lesser than 10, that is the pivot element. So they have to get swapped. So 16 and 5. You will not disturb the pivot. Pivot is just to see where it has to fit. It has to go to the right position. So you will not disturb the pivot, you leave it there. First, you will set the rest of the numbers here. So it is just like 5 comes over here, 16 goes here. So 5 came here, 16 goes here. I and j are still over there itself. Again, I gets incremented, j gets decremented. I comes at 8, but it finds that 8 is not greater than 10. So it moves ahead. It again gets incremented. J gets decremented. It found an element less than 10. So it stops here. So that was I here, which was at 5. It moved on to here. But since this I found an element less, it goes ahead. It comes at 12. It comes at 12. And then J, which was at 16, it moved here. It comes at 9. Once this happens, as I just told you that I should be greater than 10 and j should be less than 10. So these two elements have to get swapped. So I comes here, 12 goes here. Clear? So 9 came here, 12 went here. Now this is your index, right? I is at 9, j is at 12. Now I has to get incremented. J again further should get decremented. I increments, it came over here. It found that there is a number greater than 10, so it stops here. Meanwhile, j gets decremented. It found an element less than 10, it stops here. Once it finds each other, it has to get swapped, so it got swapped. Done. Next again, I has to get incremented from 15 from here. So I moves to here. When it comes here, it finds that this number comparatively is less than 10, so it will not stay here, it will go ahead still. It came over here. J again moves ahead. It found a number less than 10. All right. So it stops here. Now the conditions, the increment and decrement stops. Why? Because we kept a condition that I should be less than j. That means the index position of I should always be less than j. When it comes to this place, you get to see that I's position has increased because it crossed j. So I's index position is increased than j. J's index position reduced. Therefore, we will not do any swap. Even if you find any number which is greater or less, irrespective, you will not swap. So what position should you take for this pivot? The position of J will be considered as the right position for this pivot element. So what do? You will make this 6, because J stopped at 6. You will make this 6 to come in the position of 10, and you will push 10 in the position of 6. This is how it happens. Now once this happens, you get to see that 10 has really come to its original position, because all the elements less than 10 are to its left, all the elements greater than 10 are towards its right. So this got partition. Divide and conquer, as we have always studied. This is how there is a division and conquering going on. Division has happened over here. Now is it clear, ma'am? Any doubt? Clear? Good. Okay, now what happens? Now this part, this is one, again assume that this is one complete new set. This is one complete new set. Now this is your new set again. This is a new array, because you have nothing to do with 10 anymore. 10 has come to its place. You have nothing to do. Now you have to sort these people now. So what you will do? You will take this part as separate, this right side part separate, and you will perform the same task again. Partition among them. You will consider the first element to be pivot and check its position. Similarly here you will consider 15 to be a pivot. You will first check its position by maintaining I, J. Same procedure here, just the difference is the array size has decreased. Okay. You will get a doubt, ma'am, what do we do with infinity? You already know that infinity is a bigger number comparative to any elements here. So you will do nothing with it, because it is already in its original position. Therefore, you will concentrate on the rest of the numbers that are placed here. So what is very important whenever you're doing quick sort? First is partitioning. And then when you get this small part, again partition and swap elements accordingly, keeping in mind the pivot element. Remember this. So let us first understand the algorithm of how this part, this entire thing, how we have to write in an algorithm, right? This all parts, how did we divide and swap and all. So why did we do all this stuff? To just shift 10 to its original position, divide the array into two parts. So partitioning we did. Now let us understand how to partition. So in order to do partition, I'm going with the algorithm. Partition, what did it do initially to find out? It will take a complete array, and that you will represent from L. You will take L and H as your parameters, because that will index, it will say which is the beginning of the element, which is the last element. Therefore, the parameters that it takes, it is L and H. Now you have to find out a pivot element. As I took the first element to be the pivot element, I'll say A of L will be my pivot element. Next, what I will do, I will assign I at L place, because as I just said, I will be at the first place, J will be at the last place. So I have said L, and I will take L position, J will take H position. Then I also said that till when this complete increment and decrement happens. See, for here I'm doing do increment, while till when do you do this increment? As long as A of I, that means that I position is less than the pivot element. You will decrement. This is decrement. I'm sorry, make this as minus minus. Okay. So this will get decremented. Till when should it get decremented? As long as A of J is greater than pivot. Till when this entire increment decrement should happen? As long as I is less than J. Till here is the algorithm clear? Once you find, whenever you find I is less than J, you have to swap A of I and A of J. This is what was happening, right? The swappings, internal swappings were happening, right? So that is based upon this. And once this all is done, till the while loop is completed, next what you will do, the pivot element was in A of L. So you will say A of L to move with A of J, because as I just told, J will be showing the original place of the pivot. And then what do you return? The position. You will return the position of J. Why are you returning this? Because you should know where to divide now. So unless and until you do not know the position of this box, you will not be able to divide this. So return J is to say at this place you have to do. And then again perform quick sort on this. Individually quick sort on this. So the original algorithm becomes like this: quick sort L comma H. If L is less than H, J is equal to partition. So all this algorithm will work inside this. Then you will quick sort L comma J, and again quick sort J plus H, and J plus 1 comma H. That means it's nothing but L to J. This was L to J first. You're separating this performing quick sort. Then what are you going to do? You are going to take this part, j plus 1 comma h, to do quick sort again. So that is what is written over here. Hope you understood the algorithm. Any doubt? Once you understand the concept, algorithm is very easy. Did you understand or not? Guys, please answer. Clear? Yes, perfect. All right. So now we have to calculate the complexity of this. What is the complexity? Very easy to calculate. So let me take this complexity calculation. Rather than taking numbers, I'm going to represent index position. Assume that you have 1 to 15 elements. Okay, you have 15 elements. Like now that you have how many boxes here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now you're considering that 15 rather than 10. So if you're having 1 to 15, assume that your partition happened at 8. So at the left part, you might get 7 elements, 1 to 7 elements. At the right part, you might get 9 to 15 elements. These are not the numbers in the element. I'm talking about the index positions. Okay. Consider the index position, because numbers we don't know, right? Anything can be there in the array. Again, if the partition position is 6, at position 6, index position 6, then it gets again into 2 halves. So here you might get 1, 2, 3, sorry, at 4, I'm sorry, at 4. So it is 1 to 3 here, and 5 to 7 goes to the right. Similarly, if you come to this, assume that the partition came at 12th index position. So 9 to 11 goes here, 13 to 15 goes here. Again, this has to get quick sort runs again internally, right? So once you go into this, assume that the partition happened at position 2. So you'll have one element here. At the right, you'll be left with one element. Similarly, if you'll consider this array, if the partition happens at 4, you have one element 5 here and 7. Similarly, these two, right? But at every layer, you have n elements to be considered. But at every step, what is happening? Do all 1 to 15 elements, jitne, whatever were here, till the end also, till they become individual also, all those 1 to 15 elements exist. You're not discarding any element. But at every place, what it is happening, it is getting divided by 2 here. Here it became divided by 2 power k in this way. Understanding it? I hope you're understanding, because we did lot many calculations of this kind till yesterday, right? Power k, 2 parts here, 2 parts here. Again, had it been, if number of elements would have been more, the number of partitions would have still increased. This tree would have increased. So what do you find here? So it is going till n by 2 power k. So it is n by 2 power k equal to 1, n is equal to 2 power k, k is equal to log n to the base 2. Now, right from beginning to the end, all these n elements were existing. Now, yesterday when you have considered quick sort and merge sort, when you were seeing this, these like bubble sort, selection sort, you saw that the complete graph was only one-sided. Yes, it went only one side. Either in bubble sort, last elements were getting in their order. In the in the selection sort, the starting elements were going in an order this way. If you remember that passes that I showed you yesterday. And besides that, the other thing that was happening there is, initially you had n elements. Once the next pass came, it became n minus 1. Then number of elements were reducing, n minus 1, n minus 2, n minus 3. But over in this case, there is no reduction going on. They're just getting arranged. That is the reduction of elements going on. The previous algorithms that you studied, there were reduction of elements going on. But in now present case, there are no reduction of elements going on at all. All the elements are there at their place. They're just shifting from one place to another, right? Therefore, that then n elements exist from beginning to the end. Therefore, the division shows log n to the base 2, but the layer shows n times it is going to happen. So the complexity goes as big O of n log n. Understood? Why is it big O of n log n? Yes or no?
Yes, ma'am.
Good. Now, so this is how it is. Now, this is the best case. What is the worst case? Now, question comes, ma'am, what might be a worst case in such a scenario? There can be also a worst case. How? See, look at this. When you look at this example, you find 2, 4, 8, 10, 16, 18, 17. You, as usual, consider 2 to be a pivot element. You are doing the operations. But if you look at this, you know that 2 is in its original position only, no? It doesn't have to shift, but the algorithm is still running because I keeps on incrementing, J keeps on decrementing. Till when does this happen? As long as I becomes less than J, that means as long as this I is less than J, it keeps on incrementing, J keeps on decrementing. But we know, when we look at it, when we visualize it, you see that 2 is already in its original place, but for no reason we are doing it further. But the program doesn't know this. It cannot compare. So this increment decrement happens in this way. As long as I gets incremented, J comes keeps on decrementing and it comes over here. So when that means, where are you getting the partition? As I just told, once everything is done, the partition has to happen. J has ended here. How will you, when you partition from, sorry, at this place to pivot element and the partition element is at the first place only. So there is no array here at the left side. There is array only at the right side to be sorted, right? So how does the tree look like? Assume that you have 1 to 7 elements. If the first element got partitioned from 2 to this left side array is gone. There is nothing. All partitions are going to happen at the right side only. Understood this or not? Girls, this is a bit tricky, but you understood or not? Please let me know. Yes or no? Yes? All right. Okay. So here what has happened? This J got decremented and it came again at this place. And here the left array is missing. That in the previous case you had left and right. Both you had. Therefore quicksort was working well. You were getting a tree-like structure. You were getting this sort of structure. But now what has happened? In this case, in the current case, this left side part only is gone. Only this part is being developed. Again in this, what is happening? This left side part is gone. Only this has been developed. Again this part is gone. Only this. So this part is only existing because the left area has gone. This part. Similarly, if you look into this, this is what was happening. So in the first case it was n, then it became n minus 1, reducing, left part reduced, n minus 2, n minus 3 and so on till 1. So you know this, and to calculate the complexities you add up all these things, n minus 1 plus n minus 2 and so on. Summation of n minus 1 will be written and it is n into n minus 1 by 2. I already told that this becomes n square minus n by 2. Highest degree order is n square. So the worst case scenario is n square. Understood? So then, ma'am, how can we do this? Because if somebody gives elements of this kind and we are wasting time, we always might land up in the worst case rather than the best case. Then how do we come across this? The condition that you need to maintain is make sure that you do not keep the pivot element as your first element. Instead, take any element from the center, from the middle here, 10. Take this 10 as your pivot element rather than taking the first element as pivot. Take any number from the middle, not from the beginning or the end. That time, if you take any number from the middle, then this I and J keeps on incrementing, decrementing, then you will get at least two arrays, two different arrays that time. Understanding it or not? Is that clear? So the rule, you know what, you might get a question. How do you reduce the worst case scenario of a quick sort? So maintain the pivot element in the middle of the array rather than the beginning of the array, so that the tree gets divided into two halves. If you start doing it at the beginning, if that element is sorted, then the tree becomes only right-sided tree. If you put the pivot at the end, and if that last element is a sorted element, the biggest element of all, then again the tree goes to the left side. So it makes no sense in doing the partition. So always select a pivot element somewhere in the center, in the middle of your array. That can help you in maintaining the best case by avoiding the worst case, that is order of n square you can avoid, and maintain order of n log n. Clear, everyone? Good. Perfect. So this is all about your quick sort. So simple and easy. Only thing you need to do is just refer it once again. It is easy for you. Now, so does this mean, ma'am, does this says that quick sort is the best sort among all? Need not be the same. It is not even considered to be the best. Though it is quick, it is not the best. Next comes merge sort. Comparatively, people say that merge sort works better than all the sorting techniques. But again, as I told you yesterday, it all depends upon your kind of elements and the application for which you're using it. Now let us understand merge sort. This will finish off very quick and it's very, very easy. As in the previous cases, earlier when you did your other, like you did your binary search and then you did certain sorting techniques, the bubble sort, when you were doing other sorting techniques, you were calculating the middle, right? In binary search, you did this, right? You calculated the middle part, low plus high by 2. Same thing applies when you're doing merge sort. Okay, so here what are you doing? You are taking elements over here. I'll just tell this very faster because very, very easy to understand, not at all stressful at all. So here it is, elements like this also goes with divide and conquer as in the previous case, right? But remember, insert, bubble sort, insertion sort, selection sort, they go with passes, pass 1, pass 2, pass 3, like how we traced yesterday. But when it comes to quick sort and merge sort, it is not at all passes, it is all tree format, right? It is all in the form of a tree. You're going to generate trees in this way. So it is no more passes here. Okay, remember that. Now, when it comes to merge sort as well, you have elements. You consider the first element to be low, the last element to be high. Once you do this, low should be less than high as usual every time as we consider. Then calculate the middle element. Why are you calculating the middle element? You have to divide it. You have to do a divide and conquer, right? So you should know where to divide. In order to know where to divide, you're going to find out which is the middle element. And so how do you do that? Low plus high divided by 2. Okay. So you got a middle element. And then once you get a middle, assume that you got a middle element somewhere here. You will do merge sort separately for this array, separately for this array. So it will be like, assume that this is middle. So merge sort comes from low to middle, right? Again, merge sort comes from middle plus 1 to high. Is that clear? And once you finish that merge sort in this way, then you will merge them together. You will bring them all together to make one complete array. How do you merge? You will merge low plus middle and with high. All this, when you bring them together, they become one full array. You'll understand that here. So these were my elements. Once I found out these elements here, there are 1 to 8 elements. So 1 to 8 elements. Once I did this 1 to 8 elements, I found out that 1 to 8 below to 9 by 2, right? So when I do 9 by 2, it is nothing but 4.5. So considerably 4. So the fourth place I have to merge at the fourth position. So these elements have to get divided. So here 1 to 4 elements comes here. Look at this. 1 to 4 came here. 5 to 8 came here. Again, this got merged because you found low plus high divided by 2. That is 1 plus 4 divided by 2. 5 by 2. So it is 2 again. So 1 and 2 first 2 elements comes here. Next 2 elements goes here. Similarly 5 and 8, first 2 elements comes here. Next 2 elements goes here. Again, when you merge this, one element individually comes here, right? Now what were the elements at this place? When one element matlab first one element was 9. 9 was here. 3 got separated. 7 got separated. 5 got separated. 6, 4, 8, 2. When this was all merge sort. Merge sort ka matlab dividing using the mid. Now you have to merge, mix off. When you merge these two, you will sort and merge. So what do? You see that this one number is comparatively bigger than this. So you swap here. So it becomes 3 and 9. Similarly, look at these two parts. Okay. So here it is 7 and 5. They get swapped and it becomes 5 and 7. Then look at this part. What were the numbers here? It was 6 and 4. They have to get merged over here. So this have to swap. So it becomes 4 and 6. 7 and 8, which were 8 and 2, they have to again get swapped. So it becomes 2 and 8. Now till here, this layer is finished. Now what should happen? This 2 should get merged to become here. So when they get merged, what are the elements here? 3, 9, 5, 7. Look at this. Okay, 3, 9, 5, 7. So they get merged in a sorted order. 3, 5, 7, 9. 3, 5, 7, 9 came here. Similarly, from here as well, you had 4, 6, here 2, 8. So these elements, they again get merged, they become 2, 4, 6, 8. Now again they have to get merged. So then they get merged over here. This one along with this, like low plus high with middle has to get merged. So they come in a sort, again they check with the sorted order position. So 2, 3, 4, 5, 6, 7, 8, 9. This is how a sorted order comes. So when you push this, divide it off and again combine it. Divide, conquer with some rules and combine it, you will get the sorted order, right? So when we look at the algorithm, what do we see? We see that first merge sort, it takes low plus high. If L comma H is there, sorry, L is less than H, this should be L is less than H. Middle should be L plus H by 2. First perform merge sort, that is L plus to middle. Perform merge sort from middle plus 1 to H. Then again merge them all. So when you look at this, what do you find? First 9 and 3, you have to, 9, 3 was the one. Last, when you look at this ulta mein, when you look this in ulta form, this is how it looks. 9, 3 was there, 7, 5 was there, 6, 4 was there, 8, 2 were there individually when they got separated. Then these two get merged first, they become 3 and 9. These two get merged, they became 5 and 7. These two merged, became 4, 6. These two merged, became 2 and 8. Now this 2 has to get merged, same as this part. This part, I'm talking about this area. Okay, so this 2 has to get merged, so it becomes 3, 5, 7, 9 because they get sorted in among, again, we are writing the algorithm. How to do that sorting, you by now you might have learned. You just have to put that sorting technique program in this merge sort. Okay. Then similarly 4, 6, 2, 8, you will again sort them again. Finally, I'm talking about this now, this part, this merge. So here two arrays, they merge together and become the sorted order. Understood till here? Guys, do you understand? Yes or no? Yes. Okay. So now let us calculate the complexity. Complexity calculation same as previous. Best case, because there is no worst case here, because you are not selecting any pivot element, you're not doing anything, you're just dividing them, arranging them, dividing them, arranging them. You're doing nothing. So there is no worst case because all the elements are up and down. We are not selecting any particular element. So there is no worst case for this scenario. Only one case. Okay. So when they are, assume that you have 1 to 8 elements, they get sorted in this order. So there are n elements in the beginning till the last. Also, they are having n elements only. So what could be this? But they are getting divided by 2, like how I said in this case in the previous one. Let me go back. Quick sort. Huh? Where did that go? 1 second, I'm just going to quick sort complexity calculation. Over here. The same way tree was made down also, no? This, if you consider this sheet and the last sheet that you see, there you find no difference. It's happening the same way. So when over here, when you had in this way, you said that n, then it became n by 2. It got divided into 2 halves. Similarly, and so on, depending upon the number of elements, it becomes n by 2 power k. When it becomes n by 2 power k, the calculation is of this kind. So you call it as n log n. Same thing applies to this. Same thing is over here. Right? Any doubt in this? Guys, any doubt? Clear? Everybody? Perfect. So this ends up your merge sort. So hopefully the next week, I request you all to again refer. Please refer all these concepts once again, because you might forget. There is a chance of forgetting these things. So better remember that you have to again revise. Unless you do not revise, it's difficult. Complexity calculation is very important. I've taught you how every complexity is calculated completely in detail. Okay, so I hope there should be no more doubts in this. Probably the next week you'll start doing questions on these things as well. So refer your algorithms before you getting into the session from the next week. Refer the algorithm, trace them once again, and then work on it. That's all I can say. Okay, so Chandrika ma'am, are you
Yes,
there?
ma'am.
So I wish to end up here,
Yes,
ma'am,
ma'am.
because
Sure.
it's all done. I'll just, yeah, I'll just share this document in your group, ma'am, girls. Okay.